Okay, so broad overview real quick, just a reminder of what we're doing with integrals. There's kind of 3 steps to solving a problem with an integral. Step 1 is to figure out how to take the application that you're interested in and turn it into a Riemann sum. Recognizing, of course, that Riemann sums are double integrals. Or said differently, that double integrals are a convenient way to write down Riemann sums. Okay, so that's step 1, phase 1 of the process, if you like. Next thing is to figure out how to turn the double integral into an iterated integral. If you're lucky enough to have a domain that's a rectangle, that's super easy. If it's not a rectangle, well, then there's a whole process there, right? Okay, and then lastly, given your iterated integral, there's the actual cranking it out. Applying the single variable fundamental theorem of calculus twice to compute that integral of an integral. Okay, all right. So we did a bunch of stuff after that, several examples. This is where we left off. So here's another example. We're going to do this example pretty quickly. I just want to show you, I want to compare this example to another approach. So here we go. Step 1. Well, let's say it this way. So we're computing this double integral, and the curve, the region that we're interested in is bounded by these two curves, y equals x squared and y equals 4. So remember, this word bounded by means find the region that is actually bounded, for one thing, and whose boundary is made up of those curves. So there you go. That's the question. Make sure to interpret appropriately. Don't think that it's this region over here or something like that. That doesn't make any sense. Okay, so we're going to do the x slicing first arbitrarily, and you'll note that the x slices go from 1 to 2. I mean, here's what x slices look like. They start at x equals -2, and I think I said it wrong before. They start at x equals -2, and they end at x equals +2. So -2 to 2. Okay. That said, now, as is our procedure, we pick a value of x. We then ask, for that fixed value of x between -2 and 2, what's y doing? Well, y starts there and ends there. Now we have this process, having identified that the bounds are decided by certain points. Those points are, of course, on certain curves. Those curves have certain equations, and in those equations you can solve for the variable that you're interested in. We're interested in y here, so solve for y in that equation, and it's x squared, and then likewise for the upper bound. Okay, so why did I slice this way, though? Why did I do my x slicing first, my y slicing second, or let me say that a little bit differently. Why did I do dx on the outside, dy on the inside? Why didn't I do it this other way? Let's take the same domain now, and let's just do it the other way and see what happens. Right, let's do our y slicing first, dy on the outside. All right, well, y goes from 0 to 4. You can see those y slices. They all look like this. Right? So the first one's at 0, the last one's at 4. And then, okay, fine, for a given value of y, now what's the range of values of x? Well, for that value of y, going from there to there, which means that our bounds are determined by these points. Those points are on, they're both on the same curve. That's a little weird. They're both on this curve, which has that equation. Now, keep in mind here, at this point, we are trying to find x bounds. So don't solve for y. Why would you put a y value in as an x bound? That didn't make any sense. Right? We're trying to find x bounds. We've already done our y slicing, so we need to solve for x in this equation, and solving for x gives us these two inner x bounds. Okay, everybody see the process? Now, which one do you like better between these two? I have a preference. Yeah, I like this one better. right? No fractional powers. Not that we can't handle it, right? This integral is doable, right? But if you had your choice, I think most people would take this one. Okay, now, so what we would like to figure out now is how to anticipate this, how to see it coming, and how to, more often than not, end up with the good one instead of the bad one. And so how do you do that? Well, I'm just going to kind of think through what ultimately made square roots show up here. What made square roots show up is that I found myself having to solve for something that wasn't already solved for, you might say, right? So I have x on the inside there, even though it's not already solved for. To say it differently, x is the independent variable. I don't want to solve for the independent variable. I want to solve for things in terms of the independent variable. So I want it on the outside. So take your pick, but just think in terms of what are you solving for in terms of what, and then look at your equation and ask yourself, which one would you like to solve for? And you give me the choice between y and x in that equation. I'd rather solve for y. So you put that one on the inside. Okay, all right, so that's a point of view that you can take very often. This will make the better choice between two options. Not always, but very often. Here's another example. And again, I'm just going to do this question two different ways, and we'll compare and contrast at the end. So starting off arbitrarily, here's our domain is a triangle with these three corners. So there's our domain. And with that domain, let's start off by doing y slicing. Well, okay, so y goes from 0 to 1, thus those bounds. Now we're going to fix a single value of y. For that single value of y, lower bound, upper bound on x, right? Looking at our x slicing. And those bounds are determined by two different curves. Let me write down those curves. The lower bound curve is that curve. The upper bound curve is that curve. Now, just for focus purposes, I'm not going to go through the details here, but the punchline is that curve gives you that bound, and that curve gives you that bound. You've got a lower bound curve that gives you the lower bound algebra. The upper bound curve gives you the upper bound algebra. Details for y'all. Is everybody on board, though? Everybody see the breakdown of that one? And now I ask, what if we were to do it the other way? Instead of dx dy, what if I did dy dx? How would that change things? And, well, initially kind of no problem. I mean, I can say right off the bat that, look, x goes from 0 to 2. That doesn't seem to be a problem. I could then talk about, okay, well then for a given value of x, where are my upper bounds, where are my lower bounds, and what are the curves in question? Well, your lower bound curve is that one, and your upper bound curve is, well, it's that. And this is the problem. Look at that upper bound curve. That upper bound curve, I'm going to need to look at the algebra for that upper bound curve to figure out the algebra for my inner bounds. And that upper bound curve's got messed up algebra. Right? It's got an elbow. Right? It's got a corner in it. It's one equation for a little while, and then it's a totally different equation over here. So that's a problem. Right? And roughly speaking, you can already anticipate that things are going to go poorly with this choice of the order to slice it. It goes poorly because the upper bound curve has one equation here and a different equation there. Or said differently, we're taking one curve and another curve, and we're sort of jumping from the one to the other. Or said differently, and now what happens, how do you jump from one curve to another? Well, you jump from one to another where they intersect, and where they intersect, they make a corner. So, the geometric tip-off. Watch out for corners. Try not to slice through corners. Right? I mean, the earliest opportunity that you have for seeing this as being a problem is looking at your x slices as you slice. When you slice through a corner, you're going to have a problem down the road. Okay. So now let's see exactly how ugly does this get. I've got to break up the x, x going from 0 to 2. I'm going to have to break that into two separate chunks. I mean, first x goes from 0 to 1. I can deal with that. And then separately, here, I'll do this in dark green. Separately, I can talk about x going from 1 to 2. Individually, light green and dark green, they're both problems that individually I can deal with because individually they have pretty reasonable bounds. Let's see here. So for the x between 0 and 1, there's my lower bound curve, and there's my upper bound curve, and they give me this is the lower bound, and this is the upper bound, and everything's fine because this is a well-defined, no problem, single formula curve. Right? On the other hand, over here, for these values of x, there's the lower bound curve, there's the upper bound curve, and they give me these different bounds. Specifically, notice that the formula for the upper inner bound is different. Okay, and that is, again, caused by the fact that we sliced through a corner. Everybody see how this worked? Any questions? Everybody happy? So it's another rule of thumb for you to keep in mind, and none of this is strict or required or will always give you the right answer on which way should I slice. But we do have two rules now. First rule is slice in such a way that you don't have to solve for something you don't want to solve for. Our second rule is try not to slice through corners. Okay, with those in mind, vast majority of the time, there are some exceptions. Weird stuff happens sometimes, but vast majority of the time, this will lead you in the right direction. Okay. All right. Now, the next couple of pages here, I'm going to not spend class time on. This is all pretty straight read. I don't think you need my help to make observations like the integral of a sum is the sum of two separate integrals. They are, after all, themselves all just sums. Really, what this says is a sum of a sum is a sum of a sum. Right? And y'all already know that addition's commutative, so it's pretty clear. Stuff like that. I'm going to let y'all read these two pages. Like I say again, it's pretty straight read. And I want to go on to the more significant next things. Okay. Right. So, here's an application. Correction, here's a different application that we haven't already talked about. We've already talked about several applications. Volume under a surface, that's a graph. We've talked about how to compute the mass of something if you know the density. We've talked about how to compute the population if you know the population density. Right? A bunch of other things out there. Here's one of them. Suppose you want to find the volume between two graphs. So, in particular, there is a surface, and you can see that it is a graph of one function. Here is a different surface. You can see that it is also a graph of a different function. If I want to find the volume in between these two graphs, how would I go about doing that? Now, let me remind you, our goal, the reason I'm showing you this example, it's not because I want to know the answer to the question. Right? This example is an excuse for me to show you how Riemann sums can be applied. Right? So let's not do the obvious answer. The obvious cheap answer here would be to step one, find the volume under that one surface. We already know how to do that. And then step two, we'll find the volume under the second surface. We already know how to do that. And then we'll subtract. So yeah, of course that would work. Yeah, that would get us the answer, right? But that bypasses the intention here. The intention here is let's see how Riemann sums can be adapted to different circumstances. So that's the point of view I want to take. Okay, so looking at our problem, again, here's the two surfaces in question. Here's the volume in between. And I'm going to take that as as something that can be sliced up. Right? This weird little potato can be sliced up into a bunch of little French fries. Right? And I pose geometric appeal, but that the total volume of the potato is the sum of the volumes of the ensuing French fries. I think that's highly plausible. Right? Okay. Okay. Let me say that now a little bit differently. The amount of volume sitting over this little square, this little rectangle down here, right? The amount of volume sitting over that little rectangle, that sub-rectangle, if you add up all the volumes over all of those little sub-rectangles, you're going to get the volume sitting over the entire shadow down here. So what we have then is therefore an integral that's happening on this domain. Now students get a little bit weirded by this sometimes and say, well, yeah, but there's a gap. I thought if you were computing volumes that doesn't the volume have to go all the way down? Can you just say that I'm going to associate that volume way up there to this area way down there? And the answer is, yeah, sure, you can do whatever you want. We're writing down Riemann sums. We're just adding stuff up, right? And so all I need to be able to do is to say for each little, once I've picked a domain, I just need to be able to say that for a little piece of that domain, whatever that little piece of that domain is, I need to associate part of the answer to the question I'm interested in that I associate to that little piece of the domain, and that those things then ensuingly add up. That's what a Riemann sum is. Okay. All right. So, looking at this little piece of domain here, what is the resulting volume? Well, the volume that we're interested in there. The volume, that little piece of volume, is this. I keep hitting the wrong buttons. It is this area times this height. And I think it's a pretty easy sell that height is g minus f. Right, now let's think that through. How do I know that height is g minus f? Well, height is the difference of two z-coordinates. And look, we have formulas for the z-coordinates. The top z-coordinate is g. The bottom z-coordinate is f. And therefore the difference is g minus f. Yeah?
Will we be able to do that in the integral?
Yeah, that's going to be the next thing. Yep, totally. Yeah, so remember, our process is way back here, isn't it? There you go. So step one, figure out how to turn your application into a Riemann sum. That's what we just did. And then you're quite right. The next thing is turn it into an iterated integral, and the next thing after that is plug and chug. Right. Yeah, here we are. Okay, yes?
Is the reason you chose the area, like the area that's on the XY plane versus like the area that's on one of the separate curves?
Yeah. Was there a second half to that?
Is there a reason why?
Oh, is there a reason? Oh, I misheard you. Yeah, because I know how to do integrals on regions inside the XY plane. In fact, that's the only thing we know how to do, right? So now, you could go to a lot of trouble, right, and make a new definition of what does it mean to do an integral on a surface. And we will eventually do that for other reasons, right? And then you'd have this other additional problem of well then in what sense could I view the volume as being an integral over that surface? And that would actually be also hard, right? So it's just the easiest choice to pick this because I already have a construction that works, and because this problem actually fits really nicely with that area. Yeah. Right. Okay, so here's an example. Suppose I want to find the volume that's between these two surfaces. Here's a couple of surfaces. We've got that one. And we've got this one. A couple of surfaces. I want to find the volume between these two surfaces. Volume sitting over the unit disk. There's the unit disk. And sitting over the unit disk, we want to find this volume between those two surfaces. And that's a weird volume. It's got kind of a curvy top and it's got kind of a curvy bottom, but they're curvy in different ways. So, weird, right? Odd little shape. But we have our construction prepared. Here's just plugging in that formula. Volume. Integral of one function minus the other. Now, which one minus which one? You got to think it through. Which one's on top? Which one's on bottom? I have here a picture. You can see green is on top of blue in the picture. How did I know that green was on top of blue in the picture? Well, I refer you back to chapter 12, right? We know how to draw pictures of these things. But even more conveniently, let me observe that over the unit disk, x squared is always no bigger than 1. And that means that this green function is always at least 2. Right? Whereas, for similar reasons, this blue function is never more than 1. Right? So the green is always greater than 2, greater than or equal to 2, and the blue is always less than or equal to 1. And so even without drawing a picture, I already know green is on top of blue. Everybody follow that reasoning? Because we know x and y are constrained in this way. Okay. All right. Okay, and then here's your resulting integral. Now, I want to recognize that integral is a monster. That's a nasty integral. Let's zoom in one. Here we go. That's horrifying integral. Now you might be thinking, oh, come on, it doesn't look that bad. Look, it's just a polynomial. No, this is a nightmare of an integral. Right? And here's why. Look, the dy integral is easy. Y antiderivative, okay, sure, cool, whatever. It's just a polynomial. That is easy. But then you're going to plug in these two square roots in for the resulting y's, and you're going to have all odd powers of y into which you're plugging in, right? So you're going to have 1 minus x squared to the 3 halves all over the place, sometimes multiplied by y squared. Right? So it's a pain. It's integration by parts and trig substitutions and stuff. Oh, are y'all good at trig substitutions? Okay, all right. This is just got lucky. I reminded me. This is a topic that I think is very often undersold in Calc 2 classes. I'm a big believer in trig substitutions. If you are not strong with trig substitutions, please watch the miscellaneous topics extra video that I have on my YouTube channel called Trig Substitutions. It's a really powerful trick, and I want to tell you why it's a really powerful trick. It's a really powerful trick because this expression comes up a lot. Square root of 1 minus x squared comes up all the time, and its ilk. Right? It comes up constantly. And the reason it comes up constantly is because it comes from circles, and the world is full of circles. That's really why, right? So it's a really common situation, and trig substitutions are a really powerful trick in dealing with stuff like that. So I would like for everyone in the class to become competent, reasonably proficient with trig substitution. So again, just watch that video. It's on the YouTube channel in the miscellaneous topics playlist. Okay. All right. So anyway, nasty integral, but nevertheless, look, you could crank it out and you can get an answer to the question. Now, it turns out that there's another way to compute this integral. There's a tricky move called doing the integral in polar coordinates. We'll talk about what that means later on. We're not ready for that just yet. Yeah.
Do you remember how you found the bounds?
Yeah, okay, so that's looking at the domain here. Right, here's our domain. I have x going from -1 to 1, right, because this is what my x slices look like, and that's a unit disk, and so there's that, right? And then for some value of x between -1 and 1, my upper and lower bounds are determined by these 2 points. Those points are on this curve. That curve, you write down the equation, solve for y in terms of x, and you get these bounds.
Oh, I didn't realize the domain was the unit disk.
Oh, yeah, that's right. Cool. All right. no problem. Okay. All right. One last little quick comment before we go on. This is a hard picture to draw. You don't believe me? Try it. Right? Tough. It's a tough draw. So 2 observations I want to make. One is we don't need to draw this picture. I drew it because, visual aid and all that, right? But on an exam, the thing is you already know that volume can be computed with that formula. The only thing you need to know is which function's on top of which other function, and that, again, we argued algebraically that this function always has a greater value than that function. So, you can go straight from the question to this without the picture at all. Okay. Second thing I'll say about this picture is if you do want to draw this picture, it does take practice and understanding of certain techniques and certain observations, cute observations about how 3D drawing works. And again, I'm going to push my recently recorded drawing video that's on my YouTube channel in the Miscellaneous Topics playlist. So I hope y'all will take a look at that as well. Okay. Alrighty. Okay, heads up about a certain kind of problem that will come up sometimes. The question here is to find the volume between that surface and this surface. And notice it does not tell you over what domain. Here, we were looking for the volume between 2 surfaces sitting over a given domain. The domain is not given here. Sometimes, then, the point is, you don't need to give the domain. The domain is implicit. Specifically, that green paraboloid, that blue plane, the volume that's between those, you can see that volume right there. And you can figure out for yourself what that sits over. Right? You can figure out where they intersect, look at the shadow, and thus figure out what your domain is. All right? So anyway, be aware that that's out there. Now, there is a little detailed devil I want to talk about here as well. How do you find that intersection? A lot of people make the following argument. This is complete garbage, so don't take this too seriously. Well, this one's defined by that equation, and this one is defined by that equation. I want to know where they intersect, so I guess I'll set these equations equal to each other. That's nonsense. First of all, that's not a thing. Setting equations equal to each other, not a thing. Right? 2 is equal to 2. 7 is equal to 7. Don't set 2 equal to 7, right? It makes no sense at all, right? So complete garbage. Tempting though, because a lot of people on this question will think that the domain is where x squared plus y squared, equal to 7, and that maybe that'll give you this circle down here or something. It's complete nonsense. Does everybody see why that's nonsense? Okay, you'd be surprised how often I see this on exams. Okay, so let me show you how to deal with this. How do you find that domain? How do you find that intersection curve and its shadow? So I'm looking for certain points in the xy plane. I'd like to know x comma y's that do a certain thing. And what is it that I want to know? Well, I observe that for any given x comma y, there is a corresponding distance up to the parabola, and then there is also a corresponding distance up to the plane. And if I want to find where those 2 surfaces intersect, what I am looking for then is for points where the distance up to the paraboloid is the same as the distance up to the plane. I'm looking for where green is equal to blue in this picture. Now, does everybody see what I'm talking about in this picture here? Okay. So I want to know where the 2 z-coordinates are equal. I want to know where the green z-coordinate is equal to the blue z-coordinate. So I don't want to set equations equal to each other. I want to set the z's equal to each other, right? So specifically, in this original algebra, I want to set this equal to that. Not the whole. Dang, that's nonsense, right? I want to set that green z into that, equal to that blue z. And doing that is, no big deal. It's just a matter of writing down a little bit of algebra. This green z is already solved for. It's x squared plus y squared. The blue z, you just have to do a little algebra, solve for that blue z. Not a big deal. There it is. That's what you want to set equal to each other, right? You will get these points. You will get the bounds of your domain by writing that down. How are we doing? Everybody happy? Okay, so don't play too fast and loose with your connections between geometry and algebra. Make sure to think it through, yeah.
If they were to intersect along the x or y axis, would you then do it for x or y? Like, would you...
If they were to what now? I don't understand.
If, for instance, they were a different shape and the plane were to intercept the shape along the x-axis.
Along the x-axis?
At the x-axis.
I'm not seeing what you're asking. This may be a question for office hours. It sounds like there's some details and I'm just not quite following. So yeah, ask me in office hours, yeah. Okay. Now, and last little thing, of course, you got to actually do some algebra. Once you write this down, you got to go through and solve and see what your domain actually is. And side note, it is a circle. It's just not that oversimplified circle that, again, the naive approach would give you. Okay, all right, moving along. So I want to talk about symmetry. I think symmetry is a really important concept in multivariable integrals. Y'all have seen symmetry arguments before. Perhaps not labeled like that, but here's the argument that I think you've seen before. I hope you've seen before. And that is, if you're looking at an integral, if the function has odd symmetry, or sometimes they'll just say the function is odd. So f of negative x is negative of f of x. Odd powers of x have this property. That's the name. And if your domain is symmetric, right? Symmetric in the sense that if you have some point x that's in that domain, well then its negative is also in that domain. Then the resulting integral is 0. And this is an awesome theorem, right? I mean, we just evaluated an integral and I didn't have to do any antiderivatives, no substitutions, no integration by parts, no, partial fractions or whatever. I mean, just boop, 0. Right? 2 quick observations and we spike the football. It's a great theorem. Okay. All right. Why is this true? Well, you can. Really, the best way to do this is with a substitution. And but for the moment, I'd like to take a different point of view, which is let's think about the Riemann sum point of view on this. If our function is odd, then it's like sort of whatever's going on over here, well, the exact negative is going on over on the other side. That's what oddness looks like. And if the domain is symmetric, then it goes over just as far on each side. And the big idea then is, well, you've got, a certain amount of, let's think in terms of areas, positive over there and negative over here, and they cancel. Right? So just from a geometric point of view, I think that's very satisfying. Yeah, everything cancels. Right? Now let's forget about the geometry. Let's think about a Riemann sum point of view on this. If you look at the actual Riemann sum representing this integral, and you look at the actual terms in there, well, there's going to be a term over here, that Riemann sum, corresponding to this piece, and there's going to be another term. So for this term, we get that piece. For this term, we get that. And then over here, for this little piece of the domain, we get that. Just purely algebraic comparison. On the left side, on the right side, these pieces are the same size. Delta x is the same. But the value of the function on the red term and the value of the function on the purple term are negatives of each other. And so these two terms, algebraically, are exact opposites and cancel. And that's going to apply for, every term on the right has a corresponding term on the left with which it cancels. So it adds up to 0. Everybody on board? Okay. All right, so that's single variable calculus. Why am I showing you that? Well, because we can do something very similar for double integrals. So now I'm going to have to define some terms, right? Set up a framework. But then we're going to have a very analogous theorem. So here is the first thing we need. We need to define something called a reflection. All right, let me make a better color choice. Something called a reflection. A reflection is exactly what you think it is. It's just like, how when you look in the mirror, right, and there's the reflection looking back at you, right? So it's that, but just with points and lines. So a reflection of that point is that point. So, like I say, exactly what you think it is. And now I'm going to note some analogous features that functions and sets and two-dimensional stuff might have, kind of analogous to the previous discussion. And that is, first of all, a function could have odd symmetry over that line. And by over that line, I mean in terms of what happens when you reflect over that line. Odd symmetry would just mean that when you look at the reflection, the function's value is the negative of what it is on the other side. And that's really just a sort of a two-dimensional version of this. Here, the reflection is, we reflect a value x to get negative x. It's kind of a reflection, really. This is just sort of a two-dimensional version of that. The reflection of that x is now, it's, whatever that is. Okay. Question you might be wondering about is how do you find a formula for this? And there's two different ways you can do it. One thing you could do is you could take a chapter 12 approach and think about the normal vector to the line and components, and you could explicitly write it all out. And it's very rare that we ever actually want to do that. Most of the time, we're going to pick a line over which the formula for the reflection is geometrically evident. And we'll see some examples. Right? But anyway, it's going to turn out that these reflections they're usually pretty clear as to what they are. Okay. So that's what it means for a function to have odd symmetry. Next, what does it mean for a domain to be symmetric? Well, just like it did on the other page in the single variable case, a domain is symmetric if whenever you have a point in the set, its reflection is also in the set. That's kind of a Rorschach kind of, if you're in over here, then everything that's over here, all of its reflections have to be there as well. Y'all know what I'm talking about with the Rorschach tests, right? The ink blot, and you fold the paper over, and some people see dragons or whatever, right? So those are symmetric. Because anything over here, correspondingly, there's a piece over here. Okay. With all that set up, here's our theorem. If you have a double integral, if the integrand has odd symmetry, if your domain, now it's not just, from, negative k to positive k or something like that. If your domain is symmetric, your integral is equal to 0. Bam. And again, awesome convenience. I didn't have to take any antiderivatives. I didn't have to think about bounds and plug in and take another antiderivative, right? Nothing like that. Just two clever observations. Drop the pen. Integral 0. It's appealing, isn't it? It's a nice theorem. I'm a big fan. Okay, a couple of quick words of warning. You do need both conditions to apply. You'd be surprised how often people will make the mistake of saying, my domain is symmetric, therefore my integral is 0. No, you can't do that. You've got to make sure that it's not enough just for the domain to be symmetric. You need the function also to have the necessary symmetry. Otherwise, it just doesn't work. Yeah? Okay. Here's the other thing. It's got to be the same line. It's very important that it's the same line. It's not okay for the function to have odd symmetry over one line and the domain to be symmetric over a different line. When we're looking at, and here's the argument, by the way, when we're looking at why this theorem would be true, missed. If there is the line of symmetry that you're arguing, looking at these two pieces, right, they pair up due to how the domain is symmetric over that line. They cancel due to how the function has odd symmetry over that. But it's got to be the same line, right? If the function has odd symmetry in a completely different direction, then who cares, right? Then these terms don't cancel. So, like I say, it's got to be the same line. Okay. So make sure to always think in terms of these what I like to call landmines. These are dangerous little landmines in applying symmetry theorems. Let me pause for a second for questions. I have some examples that we're going to do in a second. Okay, just to try to persuade you as to why you should care about these theorems. So I, in sort of looking back, kind of trying to remember, the old college days, thinking about this. I did a second major in physics. And in that physics major, I hope this doesn't surprise anybody, billions of integrals. Like just tons and tons and tons of integrals. Physics has a lot of integrals in it. Right? And thinking back, trying to sort of remember, okay, how was that go? How did that go? And what sort of happened? I used this theorem, right, and its analogs, very, very often to compute those integrals and just say, that integral is equal to 0 by symmetry, right? And I was trying to estimate exactly how much, and of course it's just a memory estimate, but I think a conservative estimate is about 20%. Okay, so about a fifth of the integrals that I did in my physics major. By the way, a lot of y'all are engineers. Your futures contain lots of integrals, right? Not that different from physics in certain ways, right? So you're going to be doing lots and lots and lots of integrals, and I'll bet you a lot of them are 0 by symmetry. So from my, thinking about it, from my physics major point of view, if I remember correctly, I had to take 9 classes for the physics major. 9 classes times 20%. This one theorem took care of all of the integrals for nearly 2 full physics classes. That's an interesting way to think about it. So worth talking about, right? Worth being aware of. Worth sort of always having on your radar as whenever you see an integral, double integral. We're going to later talk about more kinds of integrals. Whenever you see an integral, it's really worth thinking about whether maybe, possibly, you could just declare 0 by symmetry and move on. Okay. Alrighty. So, right. So let's see an example here. Here is a domain, the unit square. The unit square has lots of symmetries. The unit square is symmetric over that line. It's symmetric over that line. It's symmetric over that line. It is symmetric over that line. Right? Okay, so we've got a lot of symmetry options. That's nice. Okay. I have this function here, f of xy equals x minus y, and we're going to try to compute the double integral of that function over that domain. That function does not have a lot of symmetries, but it does have one. That function is odd over that line y equals x. And the way I'm going to argue that is to observe the formula for the reflection. Once you've picked that line, if you take a point x comma y and you want to reflect it over that line, well, you get y comma x. Right? I think that's a pretty easy sell. You think about it's a 45-degree line after all. Right? And so what had been vertical becomes horizontal. What had been horizontal becomes vertical. And think through the details, but I think that's an easy pitch. Is everybody happy with that? Okay. So there's the formula for the reflection. Now again, I claim that this function has odd symmetry. The way you show that a function has odd symmetry is you need to compute f at the reflection, and you need to show that you get the negative of the original value of f. Here's that calculation. Let me walk you through the details of that calculation. First off, we have our formula for reflection. Reflection of xy is yx, so plug that in. Okay, now you got to be really careful with this next step. What is f of y comma x? The problem with evaluating this is I've got a y in the x position, and so is that y or is it? But it's kind of like it's the x here. So do I call it x? Do I write it as x? It's easy to kind of get confused, right? My resolution of that difficulty is to come back up here and just rewrite this function. I'm going to rewrite the function as to avoid confusion of variables. F of a comma b is a minus b. So let's think of it in those terms. And now if I want to compute, given this, if I want to compute f of y comma x, well, y is my a. So I have y minus, and then x is my b. So y minus x. Everybody follow? Questions about that? It's real easy to mess this up. Very importantly, f of y comma x is y minus x. It's not x minus y. Okay. Right. So y minus x. Now my goal is to show that that's the negative of f of x comma y, and conveniently it is. So, this y minus x, don't forget, the thing it needs to be the negative of is x minus y, and it is. And so this function has odd symmetry. Does everybody see how that calculation goes? Okay. All right, so domain symmetric. F is odd. This integral is equal to 0 by symmetry. No antiderivatives, no bounds to worry about. Just declare victory. Okay. Right. Integral is equal to 0. Okay. Real quick, I want to talk about the rules for using this theorem in this class. You do have to actually show me some work. What I can't take is, if I ask you to compute this integral, if you just write down integral equals 0 by symmetry, I can't take that. Right? First of all, this is a class about ideas. You haven't communicated enough ideas there. You got to give me some details. The other thing is, again, with how often integrals are equal to 0 by symmetry, I don't want anybody just throwing up a Hail Mary pass. Right? I did that myself. I scored with that technique when I was a college student, right? At least once. I was running out of time. I had 30 seconds left, and I was like, oh my God, I didn't even get to this question yet, and equals 0 by symmetry. Fold it, turn it in, score. Right? Excuse me. So, getting over a cough. Sorry about that. But, so I invented that scam, right? And so I can't let it slide, right? So here's the rules. What you have to do if you want to use symmetry, you have to tell me, first of all, you have to indicate what the line is. You have to show me what the formula for the reflection is. you have to give me the full calculation to show that the function has odd symmetry. And you have to assert and be correct that the domain is symmetric over the same line. You don't have to prove that the domain is symmetric. That's usually geometrically just a matter of, well, look at it. Right? So that's fine. But you do have to assert it, and you do have to be correct. Okay? And that does bring me to the landmine aspect of symmetry arguments. The problem is, if you claim symmetry and you're wrong, then nothing you've written down is both valid and relevant to the solution of the problem, and you've made no progress on an actual solution to the problem, and so you wouldn't get any significant, if any, partial credit. Okay, so be very, very careful with symmetry arguments. They're very powerful, but make sure you're right before you use a symmetry argument. Otherwise, again, you're going to lose out big time. Okay, out of time. See y'all later. Oh, I do have homeworks to return. Please stick around for just a moment, and I'll pass those back.